So yeah, intriguing title. I don't know, but you'll be the judge of that. So building a laser, this is what I want to talk about. This is a project I've done years and years ago, maybe almost 10 years ago. I've never had the opportunity to talk about this. I'm glad I've got this talk put together. And when I say laser, I don't mean a little laser pointer to entertain your cat. I really don't. I mean something a lot more powerful. Not quite like that. Not quite like that, but quite powerful. But there is another story here, which is this subtitle here, where we're trying to do Agile, kind of without a playbook, as I call it, without the recipes, without the frameworks and the methods that we all try to do sometimes, and we get obsessed with them. But really, I don't know, I've seen, that made me laugh when I saw this online. You know, when I see teams all the time as an Agile coach, and they're doing Scrum, and they go, Kanban. I want to get rid of all the meetings and the sprints and stuff. Yeah. And you get the opposite reaction on the other side of the fence, where people do some other framework, Kanban, and they go, oh, I wish we had more structure, more cadence, more. And all of this kind of bores me to death, to be honest. I'm kind of not interested in this, I have to admit. Because really, what I'm interested in is agility, is the ability to respond to change, and to bring customer value to the customer, right? Because that's what matters. And we often forget this because we get so obsessed with the how we work and the method and the process. So, and by the way, it's a bit of self-promotion. I'm writing a book at the moment, which is a crazy project. I wish I did not start, but there it is. It's not quite finished yet. I hope by the end of the summer, maybe before the end of the year. There's a QR code there, so if you want to get some notification, if you're interested, it's on that word value that gets thrown around all the time, but nobody's really able to actually define it. So I wanted to do a deep dive on this, and this is the result. Now, just a little bit about me. Used to be a scientist. So I got a PhD in theoretical physics. So I'm a doctor, not that kind of doctor. So if you've got health problems, don't come to me. I have no clue. Yeah, I've done a lot of programming. I was a developer, BA, project manager, all sorts of roles in companies. Worked in different domains over years and years. Been in Agile since 2010. And I also host the meetup in Oxford. So if you're around Oxfordshire area, southeast, please come and have a look at what we do. We have a session in 2 weeks, that should be good. Got a little YouTube channel as well, where I do all sorts of videos about Agile, called the Agile Broadcast. Have a look. And if you want to connect on LinkedIn, feel free, there's a QR code there. But you're not here to hear my biography. Let's talk about the laser, because that's what's really cool. So here's a diagram of the laser. It's actually quite a big beast, right? It's on the table. It was 20 meters long, right? So it's quite a big thing. Yeah. Lots of equipment on top of it. And for those who remember their science course at school, this was a pulse laser, so 10 hertz, so 10 times a second. There's a pulse. Each pulse was 10 nanoseconds, so quite short, and delivering 100 joule. But that means that you basically get 10 gigawatts of power out of this machine, which is a lot. And to put it in perspective, it's 8 times the DeLorean, just to make it clear. Right? It's a big thing. You can't quite go back in time, but you know, it was pretty cool. And that system was pretty complex from a point of view of building the control system software to control this machine. So everything was networked. So lots of switches. We had lots of servers to run the software on it. Cameras, all the cameras to look at the laser beam were on the network. Motor controllers to change mirrors, to be able to bounce the laser. Relays to switch things on and off. Lots of equipment, energy meters, spectrometers, all sorts of equipment. Safety measures, PLCs, all sorts of equipment on there. And I'll skip that because it goes quite a lot way. A lot of machines. Kind of like an Internet of Things, of scientific things, all networked. And just to give you a bit of perspective on this, there's a picture on the lab where we built it, near Oxford. And you can see the tables. Here at the bottom, you see there's all sorts of optical equipment being put. And over time, we had bigger and bigger machines. And here you can see there's like a vacuum chamber being placed. And over time, as I said, it becomes bigger and bigger and bigger. And in the end, it looks fairly industrial, right? There's big machines, not much space, actually. It's fairly cramped. There's stuff everywhere. It was really hard to actually work in that space. And big machines, like this cryo-cooling machine to cool the system down. So it became really quite big and industrial. And again, very, very cramped. There's not much space to work in there. I'll come back to that. It's important for the story. And here you can see there's three scientists working on the system. And as you can see, they're wearing a full body suit, and something to cover their hair, because it's a clean room environment. You don't want any dust to go on the mirrors or the equipment. So it's a very clean room environment. And then they have safety goggles, of course, to protect from the laser, just in case it gets reflected to your eye. You do not want that. 10 gigawatts in your eye. That is not a good idea. And the crazy thing is that we built it here in Oxford, but we had to dismantle it, put it all in boxes again, ship it to Prague, to Czech Republic, in trucks, and rebuild it there again, because actually it was made for another lab called Hylays in Prague in the Czech Republic. It was a big project for the UK, £10 million. It was a pretty decent project size. And there's a picture once in Prague in Hylays building when it was rebuilt. There's still some stuff being done. Like you can see a lot of Ethernet cables, because it was all networked. So there's a lot of cables going around. But it's pretty cool system. Now, again, more context on the actual software itself that we built. And bear in mind, this is 10 years ago, so it looks a bit dated to nowadays standards in terms of graphical interface. But this was a view of the laser path that we had. And every box is like an instrument that we had. So for example, if you click or tap on one of the devices, the beam steering, you get another screen where you could steer the laser beam, essentially. Or you could go into some parameters and change one of the mirror. You could go up, down, left, right, and move the mirror that way. Very basic control for the whole system. And we had a lot of systems. So like the cameras that were looking at the laser beam itself, we had loads of cameras. I mean, I didn't count them, but there's a lot of cameras. And you could have a view like this, where you can actually see the laser beam. That was pretty cool, too. And you could have a much deeper view of the laser beam itself with more analysis of where the laser beam actually is, the shape it has, some kind of profiling as well. There was a lot of development went into all this over many years, actually. And as I said, we had a lot of the same equipment throughout the whole system. So there was a lot of list of things, a list of mirrors that we could move, a list of energy meters. And because it was all network, we wanted to really know whether, is the thing actually online? Is it responding? So we just had this very simple sort of RAG, red, amber, green sort of traffic light thing. Which is all the colors you see here. So green, it was online and responding. Red, it just seems to be offline, there's nothing. And maybe amber, if it's online but not really acting as it should. And this is where we ended up with in a control room, which was separate from the actual laser lab itself, with a massive sort of 3x2 giant 50 inches screen like this, where we could see the laser path, and you could open a different system here. And you can see here on my mock-up, some things are blinking, which means it's not really good. But in real life, it looked like this. It was all green, of course, although not always, right? But that's how it looked in real life in the control room. Now, in the laser lab itself, people wanted, laptops and computers to be able to manage the system. And you can see there's laptops here and there, some screens here and there, but it's cramped, there's not much space. People would put their laptop on some devices where they could. Sometimes I could see them with a laptop like this, It was very hard for them to find the space to actually work. And they often had to leave the laser lab and go in the control room and come back in. And every time they had to change again. It was kind of cumbersome like this. But I'll come back to that. Now, what about Agile? Because, I mean, the laser is cool, but let's talk about, this is an Agile conference. So I want to talk about Agile a little bit. Now, I think I like this diagram because from a technological point of view, what was the uncertainty, let's say, of what we were delivering? And because we worked with hardware, right, we had to write software, control system software for a lot of hardware equipment. And a lot of the hardware was custom made, never built before, completely innovative. It was not like things we could buy off the shelf. Sometimes there were another lab, another research center building the equipment for us. So in terms of managing the project itself, it was pretty tough because basically every estimate we could come up with to build the control system for one equipment was, it's going to take between 3 days and a month, because basically we had no idea. And if you've ever worked with hardware, the manual, they never, ever behave like the manual says. There's always some quirky thing to do. There's always a delay to have because the system doesn't quite respond like they think it should. So you need to adjust for that, or sometimes the manual is just plain wrong. It's actually not updated for years or something. So hardware is tough. And the lead time, so if you have a problem, you contact the manufacturer, they take about a week to respond, and then the second week they go, I don't understand your problem, and it can take a long time, right? So in terms of technology, it was very uncertain what we were dealing with. Now, the requirements was also very uncertain because the scientists, well, they wanted to operate the laser, obviously, whatever that means. So for example, a mirror, you want to move the mirror basic functions up, down, left, right, that kind of thing. But beyond that, it wasn't really clear what they wanted. How much automation would you want? How much safety would you want in place? It wasn't clear at all. They didn't know what they wanted because they've never built it before. This is one-of-a-kind laser that doesn't exist anywhere else, right? Completely custom-made. So in terms of uncertainty, we were kind of roundabout there, I would say. Not quite chaotic, but it was very, very like, we don't really know what we're doing. And what I wanted to share was what we didn't do, what we did not do. We didn't really look at a recipe like Scrum or any other framework. That just didn't feel right because it just didn't make sense to be stuck in those rigid frameworks. And we did not obsess about being on time. I mean, it's academia research anyway. So being on scope, there's no such thing anyway. And being on time, well, everything is delayed in the public sector research centers. So that didn't really matter anyway. But crucially, what we did not do was to say yes to whatever was asked. Because, not with me in the project, for sure. Because really we wanted, again, to look for customer value, right? Not just do what was asked to do. So what did we actually do, though, if we didn't do any of this stuff? Well, let's see. So something fairly trivial, we had a Kanban board like this. Nothing special about that. But although it was actual post-its on an actual wall rather than a digital, Jira board or something. And that was nice because it was there in your face all the time. Every time we went into the office, it was just there. We didn't have to kind of go and find the screen on the call, It was just in your face. You walk in, you go, oh, okay, that has moved. Oh, cool, interesting, right? But more specifically, I'd like you to pay attention to this column. And if you can read, it says lab access at the top. And the point of that is that we wanted to be able to not just deliver the software and then go, that's it, we've done the control system software for that piece of equipment, job done, right? Like, no, we wanted to be able to go in the lab and test it with the users and see whether it actually worked. And I don't say work in terms of, does it fit the requirements, like it fits a mirror up, down, left, right. That's just basics. Of course it should be tested that way. That was the column before, right? Test. But we wanted to check whether it would actually solve the user's problems, or the scientists, what they wanted to do with it. It's not the same thing, right? So we were really, that's the difference between output and outcome. Right? Output being the thing you do, the thing you produce, but the outcome was the thing we want to achieve with that, right? So the scientists, for example, they want to move the mirrors because they want to adjust the laser position. Okay, could they actually do that, right? So the lab access step, that could take weeks because we would keep trying, keep observing them. So I would be there in the lab quite often, every day, with the full suit on and the thing for the hair and the goggles, just to observe them and see how they actually use the system. And it reminds me of what Goiko said this morning, right, about zero distance to customers, to actually observe what they do, right, and the quirky things they do. And I'll come back to that in a minute. So really, our definition of done is the outcome rich, not whether we've done the output. Right? We also had a story map. So it was on the wall as well in the office. And for those who don't know what a story map is, very briefly, it's basically a 2D backlog in 2 dimensions, where you have on your columns, on your horizontal layer, all the elements you need to do to complete the system. And then going down was how to refine the solution. So for example, we knew we wanted to be able to view the laser beam. That's one of the things we need to be able to do. Okay, what could we do? The first basic thing to do is have a camera viewer, and you've seen some screenshot earlier. Okay, but then you could refine that. You could have some kind of Bing profiling. You could keep going, right? Keep refining that system just to view the laser beam. And then you could say, well, the next step could be to adjust the laser position. All right, let's have some basic, simple mirror motor control. Okay, but then you could have some kind of automatic beam steering thing going on, right? And then you can keep going and build that map, and that's what we had on the wall. And that was really cool because it gives you this kind of strategic view of the whole system. And the way we wanted to approach this was to, number one, go as fast as possible this way. Right? So the first row of yellow stickies, because that gives you the whole system. Right? And then the users, the scientists, they actually could use the laser fully, as long as you've done all the first row of stickies there. And then on the second step, we could then start to refine things strategically, not everything, because some things just need to be basic. We just need it there, we need it once in a while maybe, and some things really needed to be really, really cool. And there we would go deep, right? And that was really a nice tool because we could have an actual strategic discussion with the scientist on what you actually want, as opposed to the traditional negotiation on scope, based on time and delays and so on. This was a lot more based on value, right? Where do we want to go really deep in the solution space? And yet we still want everything because it needs to work. We need an end-to-end solution for this to work, right? So that was really, really interesting. And that brings me to this difference between incremental and iterative development, right? So when you build something incrementally, like let's say you're painting the Mona Lisa, you're doing incrementally, as in bit by bit. Then you do elements per elements. But at the beginning, you've already decided everything about the system. You're just making it in chunks. So it's really hard to have any agility there because you've already decided everything up front. Now, if you're iterating, you're kind of refining the system bit by bit. There, you have a lot more opportunities to change things, right? To adapt. And to see when you put it in front of the users, it's not quite right. Okay, let's change that, right? But at the top, it's very hard. So we were trying to be much more iterative than we were incremental. Another aspect was trying to be, I laugh, I see myself there, as a cross-functional team, but a real cross-functional team. So what I mean by this is, so this was my desk at some point. I'm not sure if you can see, but there's screwdrivers and electrical cables and fans, because I think I was trying to see if I could cool down a little machine there because it's getting too hot. So I was trying to make a little control thing for that to have a fan, like a normal computer fan, but maybe I could just adjust it to cool the thing down. That's not the typical desk of a software developer or of an Agile coach or Scrum Master, like I was at the time. But one team, right? We could have had handoff. I could have said, hey, electrical team, please create me something to cool the system down, right? but they're busy, and then they add their thing to their backlog because it's a different team. And then we have hands-off and delays, and let's not do that. So we were really cross-functional. And then the next picture is me with the oversuit and the thing for the hair, and I was about to go in the lab. You can see behind me the control screens in the control room. And I've been known to crawl under the laser trying to pull cables as well, because I didn't want to wait. It's as simple as that, really, but I didn't want to wait. Let's be a cross-functional team. That really, really helped. So basically what we did, right, there was a Kanban board to visualize the work, okay, easy, but really the key, the magic here was to be able to focus on outcome rather than outputs, right? That was the key. And no frameworks really forces you to think that way. You've got to think about that. Story mapping, right, to strategize, that was a really good thing, and it forced us to be a lot more iterative than we were incremental, so that we could actually have some agility here. Cross-functional, no delays, no handovers, or at least minimize it, right? It was not zero delays and handovers, of course, but we could minimize it that way. So the key here was collaboration with the users. Like Goiko said this morning, zero distance, was it? Zero distance to customers. Right? And it makes me think of this analogy that I saw a couple of years ago. Oh, excuse me, my voice is a bit dry. This analogy that I really like in terms of where we are more like a waiter, in terms of people come to you with, I want this, and then you go and do it and deliver it. Right? You just do what you asked. Or where we're more like a doctor, in terms of someone comes to you, and say, I want this drug, and you go, no, wait, let's first find out what the problem is. And then I'll prescribe something good for you, because I'm the expert here in terms of what the solution is, right? So do you behave like a waiter, or do you behave like a doctor? Right? And I love that analogy. This really speaks to me. And we were definitely trying to be more like a doctor than a waiter. So when they came with requirements, what was interesting is to say, well, hang on, tell me what the problem is, and then we can discuss a solution, right? But let's first discuss the problem. Now, you remember that picture I showed earlier? Very cramped, lots of devices everywhere. And then this one, again, where you see scientists are kind of going down like this and trying to work. So imagine one of them says, I was trying to build something, and he goes, I'd really need to see what the laser is doing on camera number 5, for example. Now they would have to leave the room, remove the suit and the goggles and everything, go to the control room, look at the camera 5, and go, okay, put the thing back on, go back in. Very, very awkward. And then I saw this behavior all the time when I was there. I'm like, okay, there's got to be a better thing we can do here. That's just not good, right? So I thought about, okay, maybe we can put monitors hanging from the ceiling. Maybe. And then put Raspberry Pi behind them. Those mini computers, British made, are really cheap. You have a full computer. They're quite powerful nowadays as well. Put them at the back of the screen. No mouse, no keyboard, right? But because everything was on the network, you had those little cameras with a server behind them. We could easily kind of create like a sort of front end, right, on a tablet or a phone or something, and we could say, I want camera number A, I want it on monitor 1, boom, right? And I want camera B, and I want it on monitor 3, boom, there we go, right? And with this idea in mind, it could be that the scientist is somewhere in the room and could just look up, right, on whatever monitor is facing him. So we could place monitors strategically throughout the room so that wherever you are, you could at least see a couple of screens hanging from the ceiling because there's no other space, really. And with that little gadget, maybe that would be useful. Maybe. It wasn't in the requirements. Nobody asked for that. But I thought maybe that would help them going back and forth in and out the room all the time, which was really painful. So actually, we did do that, but just as a prototype, right? I didn't put monitors everywhere. That would take too long. I first had to test the idea, right? Do they actually want this? Is this actually useful? So put some monitors here, And you can see the laser beam, you can see the Raspberry Pi attached to them. And then some other screenshot here where with the actual laser going on, there's nothing on this monitor. And then they loved it. They thought, oh, that's brilliant. It's a really, really cool system. I don't have to go back out, and I'm losing so much time that it's really, really awkward. They loved it, but they didn't think about that, right? Nobody had thought about doing something like this. Another story I want to tell is with this thing. So this was like an automatic beam steering. So one thing with lasers is that they drift over time because of temperature fluctuations, things like that. The mirrors, they deform a little bit, they move a little bit with temperature fluctuations. So basically every day when you come in the lab, the laser is misaligned, to the point where at the last cameras of the system, you can't even see it. It's just gone, right? Because the path of the laser is really long. It's like the laser itself is 20 meters, but the path it takes is kind of convoluted like this. So at the end, it's hundreds and hundreds of meters. So a tiny change at the beginning, and then at the end, you've got potentially meters of difference where we should be with the laser beam. It's just completely gone. It doesn't even hit the mirrors anymore, right? So every day, the scientists had to kind of realign the system from scratch, every day. And it would take them about an hour, every single day. So they knew that, of course, they're experienced scientists, laser scientists, and therefore we're going to have a beam steering, automatic beam steering thing. So we made a little prototype here. There's just a laser, two cameras, a couple of mirrors, just to prototype the thing. They came up with some kind of complex algorithm where you could detect where the laser beam with the camera, and then if it moved, kind of put it back. And that was one of my first assignments. And I told you about the doctor-waiter analogy. In that case, I had just arrived in that organization. I was very much a waiter. They said, we want that beam steering. Like, okay, cool. And I just went and developed that. But it took forever. It took a lot of months, in fact, to get that working. 6 months, in fact, it took, because it was quite hard to do well, you know. And here's a screenshot. You can see the laser beam. You could look at the centroid as in the position of the beam and so on. But eventually, after 6 months, it worked, at least on this little prototype. So we went to install it on the laser in a few strategic places. I think there was 4 or 5 stations throughout the laser with a beam steering system in place. Okay, cool. And it kind of worked, okay. From an output perspective, it did exactly what they wanted. And then every day after that, I would come in the laser in the laser room, and I would find that it was off. They would turn it off all the time. And I thought, well, why is it off? Why do you turn it off? And it turned out that it was really annoying, because when they were doing their experiment, they were making some measurements, taking numbers and things like that, and then it would move right in the middle of an experiment. And then all the numbers change, and it would screw everything up every time. So they would actually turn it off. And of course, they would forget to turn it back on. So the next day, it was still misaligned. And then they still had to it just didn't really work. Now we're trying to do things where it would turn on in the morning automatically. So even if you forget, it turns back on again. But because they just forget. So once the laser beam is gone from the camera view, you can't detect where the beam is, and so you can't bring it back. So it's lost, it's gone, so it wouldn't work. So it just, in practice, it just did not work at all. And we spent 6 months on it. So instead, I came up with, I said to them, I said, look, what can I do to help them? So they come in the morning, and it's all misaligned, maybe, or they don't really know where it's misaligned. So I thought maybe we can look at each camera. So each block here is a camera. And if we detect the beam, we can, because we knew where the beam should be once it's aligned, so we could just measure the distance, right, from where it should be to where it is, and then just have a color scale, right, green to red. So red is really far, green is almost there, and then just show the system. Would that help? I don't know. I was just trying something. Because then here they could tell, oh, at the start of the laser beam is pretty good, But then at the end of the laser, it starts to be red. It's not good. Let's go and align that. So they had a head start, right? They know where to go. Maybe they would shave a bit of time and make their life a little bit easier, right? So I tried that. And it turned out, for various reasons, this was a bit of a gadget. They were like, oh, yeah, that's really cool. They were excited about it. They all tried it, but after a while, they're like, actually, it's kind of helpful, but not really. Because we still have to align everything anyway, just to make sure, because we're scientists and we want to be perfect, and we don't really, we just want to do everything. Oh, okay, fine. I was a scientist, I know what you mean. It's okay. But the point is, if I compare those three stories, so the first one with the automatic beam steering, it was on scope, right? This is what we had agreed on, what they worked on. They had thought about the algorithm and all that, and they got the software development team, me, to build it. Okay, 6 months of effort. Outcome, not good. It didn't work, like I said. Right? So that was not really good. Should we have done this? Well, no. We shouldn't have done it, really. Or we should have tested it much earlier, right? Rather than flying blind for 6 months. I mean, we were testing it from a software perspective, but we never tested it whether it would actually make sense in real life, installed in the system, used by them, by the users. That was the failure. That's why we had the lab access column afterwards. Like, no, we're not doing that ever again. We need to test this thing, right? Now, the second story about the Raspberry Pi camera monitors, it took about a week to do, easy, really. Just had to write a little client on the Raspberry Pi to show the data, install the screens. We had spare screens to test it. Didn't need to buy anything. It was just there. Took about a week. Outcome, really wonderful. They loved it. They wanted more. We installed, 10, I think, systems like that in the whole room. They really loved it. That really saved them a lot of pain. Right? Should we have done it? Yes. Was it in scope? No. Right? Nobody had asked for it. But we did it anyway. And then the third story, right, where the alignment, the color scale alignment view, right, was, well, it wasn't in scope. It was even cheaper to do because 2 days, it was really easy to do. I had all the data. I just had to put it together and make a screen. 2 days to do this. Outcome, not really good, actually, because they were like, yeah, nah. So actually, it was negative, right? Should we have done it? Yes, absolutely, because it was just 2 days, right? Absolutely worth it to test that, because we've learned that actually that wasn't the right way to go, right? Where with the 6 months of automatic beam steering and a prototype outside of the lab in a little room where we didn't test it live in an actual real setting, that didn't work, right? So really, what I'm trying to say here is, if we want to be value-driven, if we want to deliver customer value, Scrum and Kanban and SAFe and all those frameworks, they kind of help. Of course, I'm not saying they're rubbish, although I might be saying that. I'm not sure. I let you be the judge of that. But I'm saying they don't really help you with delivering value, really. You need something else. You need to have a sort of high-level ways of working, not framework, but where you have an idea, you can articulate it as an hypothesis. You might call this hypothesis-driven development. This is a thing that exists, right? Where you say, if we build this thing, we will get that result. Right? If I put screens all over the place in the lab with Raspberry Pi at the back, then it will make the scientist's life easier because they don't have to come out and come back in. And I can just measure that by asking them, hey, or I can just look at them in that case. I could just observe them to see, do they keep going back in and out just for the camera? Oh, no, they stay inside now. Cool. So you can test it like that, but really test it. Not test the output, test the outcome, right? And once it's fine, then you build it, right? So like the camera Raspberry Pi thingy, the client I made to get the laser beam displayed on it, I just hacked that together. I did really quickly. I didn't test it. I didn't do unit testing. I did all the engineering good engineering things that you normally do. I didn't do any of that because it was pointless. It was just a test. It was just an idea. Now that we thought this is good, we validated the fact that it works. Now we can build it properly. And now I got another team member, so okay, now do it properly. Test it properly, do it properly. Right? So it's a really different mindset. And of course, some ideas don't work, like the alignment screen. And we need to be able to say, no, that doesn't work, forget that, right? It's an idea, it didn't work. So we need to be able to kill bad ideas, even though they feel like good ones. And then, of course, sometimes you're not sure, right? You're not really sure. Maybe you don't have enough data, right? Because, of course, this was easy. I was there all the time. I could see what they do. In a complex, big company, e-commerce, let's say, where you don't really see the customers, or you're not able to talk to them directly, that's much harder, right? Of course. But maybe you don't have enough data. Maybe you need a better test, right? It depends. But it's basically the framework, take the term loosely, that I had in mind to be able to be customer-driven here. And really, that's it, because I'm hoping that with that little story about this cool little laser, that I've inspired you to, what's the word I would use, to be really looking for being actually value-driven and be close to the customers. Just like Goiko said this morning, zero distance to customers, and have this kind of cycle of trying things if you can, and see if it really works in real with the users. Thank you very much.